Hello again, this is Ty Warner with KISSsoft USA. Today I just want to talk about some KISSsys options and features you can use in order to generate a quick system level design. First we're going to open KISSsys. And this is the main KISSsys window. You can see I have my administrator privileges turned on. When I turn that on, it means I can actually build elements and make adjustments, etc. In my settings, I'm going to go ahead and go to KISSsoft Calculations, KISSsys Calculations. I'm going to do an iteration for torque and no additional function for kinematic calculation. Additionally, I'm going to go to Elements and I'm going to say Ask All. We're going to start out by looking at a template here. If we go down and select our templates on the bottom, we go up to our tables, and we can find our, it's going to be system settings, I believe. I'm going to copy this. Oh, default geometry is what we want. Default geometry we're going to copy. Then we're going to go back to our model and we're going to select the overall highest level folder here, and we are going to paste it in here. Okay. Now our default geometry is pasted in here. If you double click this, you can see that there's different types of settings for shafts and for all lengths in millimeters, approximate corresponding torque. This is in Newton meters. The bearing types that you want, you can specify those, the distance to the sides, etc. You can also look at diameter difference in shafts, module width, distance to shaft, all kinds of things in here. If we look at the center distance, etc. I know that I'm going to be looking at around 500-600, but we can actually change these lengths in millimeters as size factor, and we can get an idea of what our corresponding torque is going to be. If I make that a 2 and hit enter, I can see a 500 Newton meter torque is now calculated based on the size factor that I'm choosing. And you can see a lot of these other things have now updated as well. You can adjust your modules if you know you're going to have a bigger module as well, but these should be, if I put this as a 3, you can see some other diameter differentials. This I think would be in millimeters, but 118 millimeters with a module tool. If I change this to a 3, you'll just consider that module and then also the width of those gears as well. These are all things you can change later on. This is more or less the first setting of of the system. So I don't need a size factor of 3. I'm going to go with a size factor of 2. It's going to give me some shafts in this range, which is what I'm kind of interested in, and it's also going to give me these lengths. So my default geometry now is set. I'm not looking at, I'm not going to size the bearings or size the gear teeth at this point. I just want to have them generate these shafts the way they are there. So now I'm going to go ahead and close this because I don't really need it open. I'm in my 3D view, and what I want to do is I want to highlight my high level folder. I have administrator unlocked so I can make changes, and I'm going to go ahead and add a folder, a group folder. I'm going to call it GB group box. Okay, and then I'm going to close this because now what I'm going to do is I just want to size a planetary gear set, and KISSsys has a nice feature in here where it has some default templates. In this case, I'm just going to go ahead with this planetary gear stage. I'm going to click on it. I'm going to call it stage 1. And notice I have this gearbox highlighted over here. So it's going to place this planetary stage within this gearbox, this GB folder over here. KISSoff now populates this entire planetary system, and if we look at it, we said we wanted the default geometry to be like a 40 millimeter external diameter shaft, and the hub would be 90. If we go down in and close this and look at the main shaft calculation right here, which is populated by KISSsys, I can double click this and open it. Now I can see what we have for some shafts here. Diameter is 80 on this one, and I'm guessing the 40 is going to be in that pin or somewhere in there, but it's sized this now to handle the basic geometry of the size factor of 2. If you go ahead and close the KISSoff module, everything is stored within KISSsys, so no worries there. A couple things we're going to do. I want to open and expand these two shaft elements, and on the sun shaft I'm going to go ahead and I'm going to add a coupling. I'm just going to call this input, and on the ring shaft, or we're not going to do a coupling on the ring shaft, but we are going to do a coupling on the carrier shaft. We're going to add a coupling on that as well. We're going to call it output. Okay. Now I have an input and an output. This is a single stage planetary. It's defined, it's designed. Now what I want to do is I'm going to go ahead and minimize this gearbox. I'm going to highlight the high level. I'm going to add my input and output boundary conditions. So boundary 1 is going to be the input. As I hit OK, I can now filter through the element, and I had entered the sun shaft input. Right here is the coupling. I'm going to say yes, I'm going to do this at 3,000 RPM, and yes, I'm going to do a torque constraint, and I am going to, we had 503 on there, but I'm going to go ahead and I'm going to put it in foot-pounds, just because I like foot-pounds. I'm going to say 500 foot-pounds. Say OK. Again, now I'm going to add another boundary condition, which is the output boundary condition. Okay, and it's on the carrier shaft, it's on the output. And I'm not going to do any kind of speed or torque constraints. I'm going to say it's okay. I'm going to close it. Now one thing that you need to be aware of is the ring shaft, this guy right here, is supported with this support element. If you look here, it's this. We call it a KISSoff support element. And if we look at the properties of this, right-click Properties window, we can go down and see the different states. We can see that Rx is fixed, Ry is fixed. This is rotation about X, Y, and Z. We can look at the states about X. In the state of Z, this would be the vector along the vector path, so it's fixed in space. So this ring shaft itself, this gray piece right here, is fixed. It's not allowed to rotate. So essentially we're looking at a fixed ring gear type planetary system. Okay? We've defined our input and our output, and what we want to do is make sure the kinematics are working. So I go ahead and do my calculate kinematics, and I didn't get any kind of failures, so my kinematics must work, and I can double check by hitting this play button, and I can watch this. Is it going to work? Sure it is. It's working, the sun gear is working, my planets are rotating against my ring gear, and my carrier output is moving. You can see that with the arrows, etc. I hit escape. Sometimes I hit control escape and that works better. I'm not sure why that is, but it seems to work that way for me. So I have this now, and I can set this up, my input, my output. If I look at my diagram, which is this diagram right here, I can see that I have an input. This is my output on my carrier. This is my input on my sun shaft. And now if I zoom in here a little bit, I can go ahead and move some things around. And kind of get a little bit better sense of my power path. So I have a planet gear and a planet pin. That is moving around in this guy. Sometimes I would say that it can be kind of a pain to rearrange these diagrams, but really, if you take the time to understand your power flow, it's pretty important. You know that. So I'm doing it this way because then I can move my planet gear down, and I can see my power flow paths a little better. Okay, here we go. So my ring gear, I have two bearings on my pin for my planets, and those are connecting the planet gear to the planet pin, and the planet pin is driving the carrier. And of course you can see now that I have power flow coming into my sun shaft. It goes through the planet gear into the ring shaft. The ring shaft is of course connected to the carrier through the pin. You can see the pin and the carrier are connected, and of course this power then flow, there is I don't want to call it a recirculating power path, but you have a power path running through here that then flows into the pin drives the carrier. Okay, that's how it's set up right now. And you can see that we have red arrows that follow what the power flow should be, and all is good with the world, it looks like. So that's our flow diagram. Now what I'm going to do is I've already decided what, in terms of RPM and torque, I want to size this thing. And the way I size a planetary set is it's pretty nice. We can go ahead and if you click on the planetary calculation, you can right click and gear size. And it'll give you these default numbers, and maybe you need a 3.1 ratio. You're going to stick with a 20-degree pressure angle because maybe that's what kind of tooling you have is in terms of that, but maybe you want a 25-degree helix angle, okay? And that might be too big, but we're going to try it. So we hit OK, and the system now is going to go through and it'll do a quick mini design, and it will provide a suggested sizing, okay? Now you see, of course, your ring gear is bigger than the ring shaft, and your planet pins are outside your carrier. What we do at this point is we can double click the main shaft, and it'll pull us into this main shaft. And now all these shafts are coaxial. So we can see that we have to make some changes here. And one of the changes we need to make is for the ring gear. And on the ring shaft, sometimes it's really nice to just kind of close these other ones. So you just have the ring shaft here. We can see that we have a 350 to 50 millimeter diameter on that, but we're going to make it 550. Okay, now it's getting there. In our inside diameter, and I'm assuming that you know a little bit about the shaft module, so I'm just going to go ahead and make this 450. No, that's a little too big, because you can see our ring gear isn't quite that big a diameter. Maybe we make it 400. Now our ring gear is stationed within our ring shaft, and this is they're considering this a body. So now we're holding the coaxial ring shaft and the ring gear. Okay. Now what we need to do is we need to look at the carrier. Now the carrier needs to be wide enough to handle we have to locate the pin. And if we look back at that KISSsys system, we can see that this carrier obviously is not wide enough for that. So what we're going to do is we're going to go ahead and bump this up. 400 we think is too big, so maybe 350. And then our inner diameter, we're gonna bump that up to maybe 300. We'll say 300 at this point. And then we're going to close this because everything that we do here is recorded in KISSsys. So we close this and we do an update. Look at that. Here's our pin. We wouldn't have to go quite as wide. We could go a little bit narrower. So if we go back to the main shaft and we say let's make this 300, and we're going to go ahead and make the inside 280. We'll see how that shakes up. Let's have a look. We hit refresh on here, and there's our pin. It's on the outside. We can see our bearings. We can see our gear body shaft, etc. And we can also see that our ring is now holding our ring gear. Okay? And we can play with the widths of this, and we can actually define our shaft pretty well with inside there. But we've actually sized this system now to handle our inputs. And if we go to our geometry manager, our 3D graphics, and we say I want to look at solid elements, and I want to see a cross section in here too, just kind of get an idea of what it looks like. And I say okay. The program is now going to update this 3D representation. It won't be exactly what the final is, but now look, we have a pretty good idea of what our sun gear looks like, our planet, and our ring gear and how they mesh. And this has been sized. And on our planets now we've got two bearings. We can add bearings in here. We can remove bearings. We can make this planet or this planet pin be supported on one side or both sides in that respect. So what we've done here now is we've sized this system for our inputs. And if we double click on our planetary calculations, it'll take us to KISSsoft and our planetary module. Okay? And we can run a calculation here. It's giving me a couple warnings, but we're consistent yet. We can see that we have some pretty good sized safety factors. 103, 10, 3. Flank safety is down, but and if we look at our rating, it pulled in our information here. Look at our torque and our speed in terms of the planet carrier. But we can change this to the sun gear, and it updates. So if we change this back to foot-pounds, if we just right-click on that, foot-pounds, 500, 3,000 RPM, 200. Let's make this horsepower because, yeah, we like horsepower. We can see that we're at 285 horse, 500 foot-pounds, 3,000 RPM. We have an application factor of 1.1. This would be a system default, but we can change this. And I can show you how we change that pretty easily. But now we want to fine size this, because right now we're looking at a module of 4. And what happens if we come in here and we fine size this? So we had 3.1, and maybe we got to be within, this is our nominal ratio, so we're doing a fine sizing. Our nominal ratio is 3.1 plus or minus 5%. Maybe we want to do 2%, right? And maybe we want to look between 2 and 4 on the module, and maybe we want to go by 0.5 module steps so we can look at some different applications. We're going to leave our pressure angle the same. Maybe our helix angle can go from 19 to 25 by 0.5 degree increments. Our center distance, we say that can be Pretty much anything, anywhere from maybe 70 to 230. We'll go by 1 millimeter increments. Maybe we'll go by 0.5. Now that's a big spread. We'll go 140 to 230. That could, better probably bump this up to 5,000 maybe. And then we'll look at our profile shift is good. We really don't have anything here as far as number of teeth. We're not going to define what those are. And our face width, we're not going to define what that is. We just need to make sure that something will work here. So we look at our conditions too. We don't want integer ratios because that's not a good thing with this planetary gear set. And we want to make sure we meet our safety factors. So we're going to suspend results that don't meet our safety factors. And we're going to check to make sure mounting the planets is possible. Okay? So we've set up basically a quick DOE, and this program will now calculate some different solutions. So I hit calculate, and it's going to find size. It might take a few minutes because I have a lot of variables here, and there's going to be quite a few calculations. But at the end, you'll be able to look at all of the safety factors in the root and the flank, and also the ratios, the face widths, and a lot of other information that you might want to use to try and get your best fit. Again, you might need this if you're trying to shake out some ideas. If you have a package size requirement, or if you're just starting from fresh and you're trying to figure out the best thing you can do to get these things to to work in a good manner. It's not going to keep you from going through and specifying bearings and finding out if your bearings are going to live and your shaft frequencies. You'll still have to do that. You can do it in KISSsoft and KISSsys, but you'll have to open the main shaft module through KISSsys, and then you can run your calculations there and size your bearings. I find that's very easy. You might have to do some shaft design, but that's all right. So our fine sizing is almost done. More solutions but not calculated. So we got at least 5,000, right? And so here we have all this information, right? And what we might want to do here is look at a graphic. So we click on graphics, and we're going to look at a couple different things. On our horizontal axis, maybe we need to look at our root safety. Minimum root safety, okay? And on our vertical axis, maybe we want to look at our minimum flank safety, okay? All right, and then in our color scale, we might want to look at, in this case, normal module. All right, so we probably don't need to have root safety up in this 8 range, and we probably are fine with not having safeties up in this 3.75 range. So what we want to do is, I got a phone call coming in here. What we want to do is now okay, so we're back. My phone stopped ringing, and now what we're going to do is we're going to grab one of these. Let's just say we'll just grab 4508. So if we go into here in our results, let's see, we ought to add in our number 4508. Show hide columns. We want to know what the number is. Okay. Let's see. We want our smallest. This is our ratio. We want this total contact ratio. That might be something you're interested in. Profile shifts. helix angle, face width or something you're probably interested in, face load factor. I'm just going to get rid of some of these under load. Torque, power. Kind of want to whittle these down a little bit just so that I can see them a little bit better. Pressure angle, we're not too worried about that. We know it's going to be 20. Safety against scuffing, we'll say okay. I think we said we wanted, which one did we say we wanted? We wanted 4508, I think it was a number. I can zoom in here and see a little better. Let's see here, we're going to move this. 4527 we'll grab. So we'll go back to our results, put these in order, scroll down, 4527 we need to find. There we go. We're going to accept that, close it. We can see that we have a little bit better balanced design here. We're not looking at things that are ginormous and outside of our realm. So we have some nice safeties in here, maybe a little higher than you want. You can always go back and do more work on it. We had to calculate. We still have some warnings, but we're still consistent. So I'm going to go ahead and close here. I'm going to update this. And we should see the geometry updates take effect. Here we go. There. We have a little finer pitch. We might have to do some adjustments to our carrier, but we have a finer pitch design. Depending on what your package size is, that's fine. What we're going to do now is we're going to, because we're interested in those safety factors, but we want to bring those into the in a KISSsys, so we don't have to go back and forth and open those up. So what we do is we run into our template, we look at our tables, we find a user interface. We hit copy this, we go back to our model, we go on the top level, and we paste it. Okay. Now our user interface is going to be empty, but we're going to populate it quick. So I double click the user interface, and then what I do is I go ahead and I show the properties here of my plant system. So what I know for sure is I have speed, torque, and power. Now this is going to be in the program default, which is in Newton meters as far as that is, but we have an input, we have an input, output, to start with, and I'm going to go ahead and put a ratio in here because I want to know what that ratio is as well. But on my speed, I go ahead and I grab the input and I right click property windows, so now you can see our properties. And I just hover on the speed and I do a right mouse and I drag this over to this cell, and I'm going to insert as a reference because I'm going to be able to, as a red dot reference, I can actually change this right in this sheet. And as far as the torque is concerned, I'm going to do the same thing. Insert as a reference, and my power is going to be an expression. This is in kilowatts. So if you want to convert this, we can definitely do that, but I'm going to go ahead and leave it in kilowatts at this point. Output, same thing. We grab the output element. Instead of this time, we're going to go ahead and move it over. We're going to do it as an expression because it's a calculated output. The torque is also an expression, and the power is also an expression. The ratios, Now the ratios are going to be a little different, because what we need to do with the ratios is for the speed, we need to calculate input speed divided by output speed. So I'm going to do a Control C. I'm going to insert a real. To type it's a real thing, and I'm going to paste that in, and I'm going to divide this by the output speed. So you have to have the correct convention, naming convention, which is right here, the path, which is the same thing, okay? Input, output, it has to match these names. Otherwise you'll get a funky thing that shows up and says doesn't work. Now I have my ratio. I can do my root safety, and I can do my flank safety. Oops, I wanted to say SH. SH, flank safety. Okay. Then I open these up a little bit so we can see, and then we can do sun gear. We can do planet gear. Now we can do a ring gear. Alright, now what I'm going to do is I'm going to grab the safeties of these in this calculation, the Planetary Calc. So I click on it, I right-click Properties, and now if I filter down to SF, which is my root information, there we go. We can grab the information that we want. So SF1, this is going to be the sun gear, and I do a right click, and I drag this into the sun gear, and I do it as an expression. The planet gear is SF2. Now we have SF21 and 22. This would be the mesh between that and the sun, and this is the mesh between the planet and the ring gear. We're going to grab the minimum, which is this one. And then the same for 3. Okay? And we're going to do the same thing for the flank safeties. Insert as an expression because it's a calculated value. And there we go. Now I can change these values. If I make this 800, I can do a calculation. I'm going to do a KISSoff calculation because that's where the meat of the calculations are performed. I go ahead and hit that. It calculates. We didn't get too many differences here, did we? Oh, it's still calculating. There. Now we had some changes. Maybe if I bring this down to 2000 RPM, and then I hit calculate, it's going to run the calculations. There you can see that our safety has changed. And you can put any variable you want in here by moving that over for whatever is important to you when you're sizing these things. You can bring shaft calculations if you wanted to know your shaft. Forces, torques, bearing, lives, all that. You can put that right in here too. You can actually even put in different buttons and stuff, but that's for a different time. But this is a real simple way to size a planetary gear set, a stage, and you can see it doesn't take very long, and you can size this and get the power you want and get a package size you want. I'm Ty Warner. Thanks for watching. We'll put some more of these out so people can get more, get a little bit better feeling for how this is going to benefit them in their engineering value. Thanks again for watching.